Welcome, everybody. I'm Paul. I work in Oracle in the Java Platform Group. This title is buzzword compatible, but I do promise you there is some substance to this that I hope to persuade you that we're building out a platform that has the facilities to build out machine learning libraries and machine learning applications. So let's plug in and go. So if you saw Mark's keynote, two primary goals of Java have always been to improve developer productivity and program performance. And if you look at it from the pain points of AI, that there's specific demands and improvements that we could think about towards those goals with respect to AI-like solutions, or HPC-like solutions, or big data-like solutions. They meet the demands for AI, these features that we're looking at, but they're also more broad. We're not going to specialize just for this narrow vertical. We're going to ensure these features are widely utilizable in other areas as well. And that's, I think, in one of the successes of Java is it doesn't narrowly sort of focus on one particular area. Like, we're not going to add XML support directly in the platform. As an example, I think Scala made that mistake because these things change over time. So the features I'm going to talk about, the features that only we can do in OpenJDK, Oracle, OpenJDK, the community there. They often require updates to the virtual machine, the language, and core library APIs. And crucially, some bridge the gap between the Java world and the foreign world. There's a lot of code out there that runs very well and executes very efficiently that we should be able to reuse if we can, and not reinvent it or re-implement it if you don't want to. So there are 4 features I will talk about in general that I think are relevant to AI that were either in the Java platform or are future features that may end up in the Java platform. So the first one we also mentioned at the keynote was the foreign function and memory API in Project Panama. You can use this for 2 things. One is to optimal utilization of off-heap memory between the JDK and something outside it. Zero copy is extremely important in some cases. And also better interoperation with native libraries than in JNI, like Mark showed you. So optimal utilization of memory is extremely important. Efficient productivity to how to get access to these native APIs is also very important. Next up, we have the vector API in Project Panama as well. And this effectively gives you SIMD programming in Java for optimal CPU utilization. You can think of this about enabling better number crunching. And what do machine learning things do? They crunch on numbers, often embarrassingly parallel dot product, using some clever floating point sort of representation of that someone invented. And then there's value classes and objects in Valhalla. This will give you optimal utilization of memory on heap. And crucially, will enable more kinds of number. So we can think about float 16 numbers in the platform, for example. Or someone outside could add a bfloat 16 number. And it would look like a number to the existing numbers already in the system. And then there is a feature called code reflection I mentioned at the keynote, Project Babylon. And this gives you interoperation with foreign programming models. Such as, what's a foreign programming model? Well, it's a programming model that you code to GPUs like CUDA. Or it is the ONNX programming model that represent ONNX machine learning models. Or it's auto-differentiation of Java code. It's stuff we don't specify in the platform in terms of how it behaves. And we do not want to embed in the platform how ONNX models, GPUs work, how auto-differentiation works. We want to up-level this to let libraries do that kind of thing instead. And so this enables utilization of diverse hardware and better number crunching. It's all about number crunching. It's all about using hardware. It's all about efficient use of memory. And these things are general. They're not just related to AI. So what we're adding will help AI, but it's all broadly help the platform in terms of its efficiency. So the supposition is, I believe this to be true, Java is already mostly everywhere that AI needs to be. Do you agree with me? Maybe, I do. I would say that it's more so realistically for deployment of AI models than their actual development. That's true, most of it goes in Python at the moment. But I believe if we execute well on this, that we should anticipate that all AI shops grow up to be Java shops. Now, if you've heard this play on this, there was a blog by James Governor from RedMonk, and he said that I think it's all web companies grow up to be Java companies. So I believe that we can make this happen, that all AI companies grow up to be Java companies. A noble goal. May not achieve it, but I think we can get some of the way. So is it possible to build AI solutions without these features? Yes, of course. But it is harder to design, develop, maintain, and evolve. It's harder than it should be. So we need to address the pain points to make it easier to do so. So if there's one thing that you could take away from this presentation, is that the features I said, and also other features in the platform, interconnect, kind of greater than the sum of the parts. And I think this is enabling developers to build really powerful libraries and applications. I'm sensing this myself. And anecdotally, I'm finding that the modern Java platform is becoming really good to prototype these kinds of ideas with these features. Now, I understand these features. I can rapidly prototype them, but I'm seeing other people in our groups come in and onboard to these features rapidly and be able to make progress. And so that's not just these 4 features I talked about, but it's the language enhancements, it's the API enhancements. It's all coming together into a platform that I think is really powerful and can be used for AI solutions. So here's some examples I will go through on leveraging on features relevant to AI. So one area is what is Java doing for GPUs? I'm not going to talk about this because Gary Frost over in the audience there is going to talk about this in the next session. And I've given the session details here. This is the Heterogeneous Accelerator Toolkit. And it's, we're thinking about how we can leverage GPUs in the architecture here. I think we've nailed the general architecture of how to solve this problem. And it uses code reflection and the FFM API. I'll show an example of Llama model inference developed by someone from the Graal team in Oracle. And this uses FFM and the vector API. I will talk about an anomaly detection example implementing something called MSET2. It's a proprietary algorithm from Oracle, so I can't describe the details, but I can describe generally how it works. And that uses FFM API and the vector API. And as I showed in the keynote, there are ways to develop machine learning models in Java and execute or infer them. And that's what I'm calling ONNX script for Java that I showed. And I will show that demo again and more details in the code. And maybe it's an opportunity to ask further questions about that if you watch the keynote. And this uses code reflection and the FFM API. Of course, they use other things too. But this is, you can see the two coming together, especially code reflection and the FFM API combined together to create a really powerful solution. So Panama. It's a way to interoperate with code and data outside of the Java runtime. It's been final since Java 22. And you can go to inside.java and see links and blog posts related to Panama. It's a faster, safer, more productive way to interoperate with foreign native code and libraries, as Mark showed in his keynote, than the existing alternative, which we have is JNI. I don't want to code in JNI. It's a pain in the backside to do so. But I'm quite happy coding using the FFM API. I'm productive in it. I am not productive in JNI, and I'll probably introduce more bugs than I want while trying to do so. Combined with that, there's a developer productivity tool called JExtract that can generate pure Java bindings from C header files. This is the developer boost that you get with this tool. It's very good, and it really speeds up the mechanical part of getting to interface with native libraries if they have a C header file. I don't have to write all the binding code. And that leaves me time to do all the creative parts instead. Here's an example. I built a matrix API and interoperated with the Bliss native linear algebra library. Bliss is a library that has won a lot of awards for its robust and high-performance implementation. And we've worked with Bliss developers. Our Oracle Labs has worked in collaboration with the Bliss developers to improve this API. Excuse me. So you saw a similar diagram I showed at the keynote. So we have Bliss on a native layer. We use the foreign function and memory API. We use JExtract to bind to the Bliss header. It generates some code to us. And then we implement on top the matrix API, like so. And that matrix API, then you can do all sorts of linear algebra with it. It's very straightforward. Here's an example of using this. If you were writing in C, this is how you would code using the Bliss API. So this is C code, ordinary C code. What it's doing is it's creating some Bliss objects for the matrices and filling them in with data and then doing a matrix multiply on them and freeing up the objects afterwards. It's fairly straightforward, but who wants to write code like this? I don't. Now, if you use the FFM API that's produced from JExtract, in effect, what you're getting is a C-like idiom in Java. So this is the equivalent program written in Java using the binding that Panama generated. Instead of using objects on the stack, I have to allocate them on the heap, allocate them on the native memory. So I allocate the obj structures which describe the matrix. I then create the actual matrix with all the elements, with the size of the dimensions of the matrix, and then I fill them in. In this case, I don't have to fill the matrices that are already zeros because the Panama APIs already did that for me through allocation, whereas in the C API, I had to do that. And I can call gem, but I still have to free up the objects that I allocated explicitly through Bliss. I can hide all this. I don't need to deal with this. I can hide it around a matrix API, where I create a new matrix with the sizes, I initialize them, or I get constant matrices of size 1, alpha and beta, of matrices of 1, and I initialize them, and I just call gem, and I free up the memory through the try-catch, like that. So you can see how we can write like C, but we can wrap it around in idiomatic Java code that everyone understands. And now I can start doing linear algebra. What is linear algebra? Matrix multiply. There's other stuff too, but it's fundamentally down to that. And I can call out to the Bliss native library and zero copy memory. There's no cost to it in terms of the memory copy, because all the memory is held natively on the heap, held natively, not managed by the VM. So the VM gets out the way, and I can leverage Bliss's very, very efficient matrix multiply algorithm. Does that make sense? Yeah. So onto the vector API. So the vector API is really a low-level API that you can explicitly express SIMD computations. And you can leverage effectively the hardware on the CPUs, that is the vector hardware, that executes stuff in parallel instead of in sequence. So it's a cross-platform API. You can think of it as a bunch of intrinsics. And if you've ever come across Google's Highway library in C++, which does the same thing, it's very similar. So when you write code using the vector API, it maps closely and compiles to CPU SIMD instructions directly. And so you can get data parallelism from it through this explicit programming model. And this is an API that is in incubation, but is used today, I believe, in production scenarios. Even though it's incubating, we don't tell people to do it. We don't stop people either. And it will exit once value classes are ready, because we can't talk about vectors properly as values until we have Valhalla Jet 401 in. So we're waiting on that, and that's why it's incubating for quite a while. But through that incubation, We have got great feedback. We've improved the API, and we've drastically improved the implementation, and we're still doing so. So I'd urge you, if you're interested in this, to experiment with it. Write benchmarks, write applications, and give us feedback on what works and doesn't work so we can get that feedback loop and improve it. With this, we can implement high-performance data parallel algorithms in Java, such as dot product and matrix multiply, which are the core of the machine learning algorithms. But we can also do other stuff. We can write efficient UTF validation, or vectorized arctangent, for example. So there are all sorts of algorithms that are amenable to this kind of data parallelism that compilers can't auto-vectorize or do so reliably. I'm going to show a demo. Probably many of you have heard of llama models and Hugging Face and stuff like this. A developer from the Graal team at Oracle, he wrote a Java implementation of Llama 2 by Karpathy. And there's a link there to it. I may show it in a moment. And basically, he implemented it using it, and he improved the performance by the dot product. And he changed it from scalar code, and he used this as a vector API instead. And so matrix multiply is implemented by multi-threading of the dot product. It's primarily a test case to improve the runtime compiler, in a sense, that it tells us where there are bottlenecks and where there aren't, including in the vector API or in other cases, so we can improve it. It's something that possibly will never compete with the highly optimized C implementations or hand-coded PTX implementations on NVIDIA, but it might be good enough in the future for you to run if you don't want to depend on native stuff or you don't want to depend on other exotic hardware. We may be able to close the gap over time, and hence why this test case is useful. So I can just show you some of the code here. It's in one file. It's huge. This is not how you should normally develop stuff, that's for sure. But we can see where the vector stuff is coming in. Let's see. Is it dot product? I'll show it. So you can see it's using memory segments. And you can see the dot product should be somewhere around here. Where is it? Let me just, I didn't prepare very well for this. Vector dot. There we go. Explicit vectorized FMAs and reductions based on the sizes. That unrolling and reduction produces a vast boost in performance. And I will show you that boost by actually running it. Okay. So what I'm going to do is I'm going to run this. First of all, I'm going to run it without using the vector API, like so. So I'm going to run this llama model using this Java implementation. And I'm going to ask it a question: is Java good for AI? What might you think the result might be? So I'm running it without the vector API first, and I'm waiting, and I'm waiting. And I'm waiting. This is. Oh, it's doing it. It's really so. Look, Java can be a good choice for AI developments. But now that but is doing heavy lifting. I'm going to stop there. And then I'll run it using with the vector API, and ask the same question. Of course, every time you do it, you get a slightly different response because of the temperature, the randomness that comes in. But you mostly get the same thing. Let me expand that window a bit. If you can't see it, I will zoom in. It's going. So we loaded the model at boom, 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 boom. And this is almost human readable speed in a sense. And that's just switching to doing the dot product more efficiently. And I don't have the activity monitor showing, but it should show the number of threads popping up because we're doing multi-threaded execution like this. So, do machine learning models get this right? I don't know what was this trained on, but I will go back and show the text in a moment when it completes. Okay. Pros, yes, 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 yes. Cons. Performance. Java is an interpreted language. Well, kind of, but that's not kind of true in some sense. Memory usage. Java's garbage collection, kind of, but we just saw improvements to garbage collection and we can go off heap. Limited support for parallel processing. That's utterly nonsense. It's got almost all of the cons absolutely wrong, which is infuriating. And it says, but it's mostly correct in areas, but it's just, okay, you could choose a better model, it might get it more accurate, but that's just drives me nuts. So that's what we're dealing against, possibly in the industry as well. But it summarizes it reasonably well, that it can be a good choice and depends, and of course, it's just very general. But you see, the point being is not that this is right or wrong, but the fact is that it got a huge boost in performance. So from 1.3 tokens to effectively 15 tokens per second. And also, I actually modified this code. Let me go back. I think the original code was using JBang. And so I just removed the JBang, and I just used the Java source launcher. So I didn't compile this code explicitly. I just ran the source and used the Java source launcher directly, and it compiled it in the background. This is a kind of thing, it's like a scripting thing. It's just one less thing to do. And I think that's really powerful as well. This on-ramp thing, I think, is going to help people prototype more, like me. We say this is for beginners, and it's true, but it's also for us just less friction to do stuff. All right. So another thing we've experimented with the vector API is we looked at what Bliss did in terms of matrix multiply. And we wanted to see, can we do the same in pure Java as an experiment, just to see how close we can get. So we started this experiment. We don't know whether we'll complete it or whether it'll turn into benchmarks. Raffaello from the Oracle team, Java platform group, implemented the Bliss algorithm using the vector API. We can have a quick look. Now, what I showed you with Llama and the way it did the dot product and the multi-threading is not the most efficient way to do matrix multiply computation. The Bliss algorithm is way, way faster. And the kernels, the vector kernels, are more sophisticated and sized to the hardware and unroll and pack and jam the data very cleverly to get the maximum performance or throughput through the GPU. And in fact, it becomes a memory-bound problem and a CPU-bound problem when you do this right. So he wrote some code. You can look at it. Here, we can see that he's written some kernels, for example, on the Apple M1. And we see the way the vector API is used. This is how people hand code using vector intrinsics in C and so forth. Or we can auto-generate this code too. Sometimes, if you're clever, you can auto-generate these things. But the kernel is very different to the one I showed you in the Llama CPP example. There's a lot more unrolling and cleverness in how it's doing the FMAs and so forth. So it generates a really efficient piece of machine code at the other end. And then you have to wrap it around efficient copying of memory so that the memory is aligned just right for this kernel to work. So it's quite clever, and there's like about 7 or 8 loops that go on to get this to work. But I think we could speed up the Llama implementation in Java if we use this kind of technique to get even faster. I don't know, maybe double, triple, perhaps. I'm not really sure. But it would be a worthwhile experiment to see how far we can push it. Oh, I forgot to do my timer. Okay, I'm 25 minutes in. All right. So we can do Bliss-like matrix kernels using the vector API in these experiments, and we can push these experiments further and see how good our runtime gets. There's also, in the matrix API, I showed element-wise kernels, which means if you want to multiply two matrices together, not a gem, but multiply the elements of each matrix together, you can do these element-wise kernels. And we can enhance the matrix API with unary, binary, and ternary element-wise operations with NumPy style-like broadcasting that accept lambda expressions for the element-wise operation. At the moment, I implemented this by hard-coding kernels for those lambda operations that operate on scalars. But in the future, we may be able to use code reflection to transform the scalar code into vectorized code. So developers don't have to write to the vector API. In fact, most developers should not. And the SIMD execution is composed of multi-threaded execution. And multi-threaded also that pins the threads so we don't get threads being scheduled across CPUs and then having to copy memory across from one cache, CPU's cache, to another CPU's cache. So we can use native Bliss for the ON3 operations like matrix multiply, matrix inverse, and we can use the vector API for the notionally ON operations on the CPU directly in Java there. And I think that's a really good balance. And we implemented this in the matrix API, which is on GitHub, and you can see how it works. And we use this matrix API. It was just a prototype in a sense. And then we implemented an application on top. It's called MSET2. It's, that I briefly mentioned, the anomaly detection. So we implemented a machine learning algorithm for anomaly detection using this matrix API on top. And we were remarkably productive doing this, so much so that it started to be used in production. And it was like, whoa, hold on here. This wasn't designed for this, but yet they're getting really good results out from it. So MSET2 is basically a machine learning algorithm capable of detecting faults in time-based systems, and it was originally developed for nuclear power plants. And so if a nuclear power plant starts going wrong, you want to know pretty soon so you can intervene and fix it before it gets costly or dangerous. But this can apply to other kinds of things, airplanes, cars, data centers. In fact, Oracle's been using it in its data centers to detect when machines start behaving in ways they shouldn't. For example, a hard drive starts misbehaving. You want to know kind of before it really falls over so you can get in and replace it to minimize customer disruption. So in that architecture diagram I showed, we implemented a really quite efficient implementation of MSET2 using that matrix API in Java. And it was, as I said, it was used in production scenarios. And it supports really large matrices. So we're not bound by the limitations of the size of Java arrays. We're allocating off-heap. We can allocate massive off-heap matrices. And we can zero copy between the Java runtime and the native code. And so it was actually better, turned out to be better than other implementations written in CUDA, MATLAB, not hard, and Python using NumPy. And it ran really well on AMD Zen systems. We maxed out the CPUs on AMD Zen systems and the vector units. And in this case, it was economically competitive to GPUs. So not everything needs to run on a GPU. The cost of copying data over to the GPU and back can impact how fast it can go. Those copying costs can be expensive. And that's why it became economically competitive in that regard. So this turned out a surprise to me. I didn't expect this. And the fact is the Oracle Labs people who develop and enhance MSET2, they started using our Java implementation, binding it to MATLAB, and calling out to the Java implementation because the MATLAB implementation was too slow for them. So that's a win. Here's an example. I just thought I'd show a quick example of what we did in the Matrix API and how we used it in MSET2 without disclosing some of the details. So this is basically an algorithm that calculates the standard deviation of columns of data. So assume we've got the data, we've got the mean, calculated those columns, whether it's bias corrected. We can do a reduction over that. First of all, we can say, well, what am I going to do initially to hold the data for this reduction? What am I going to do to finish it? And what am I going to do to accumulate all the data in the columns? And so I'm using a double array to hold the sort of the sum of the squares and the sum. And then afterwards, I use that data at the finish, like so. This highlighted in yellow is the one you want to optimize. So I could use code reflection to translate that into vectorized code and then run it on linear pieces of memory on the columns. And it will run really fast. Now, we don't have the ability to do code reflection on this yet, but it's something I want to explore. You can do it slightly differently. If allocation is causing you issues here, you're holding, oh, we're allocating, we can't optimize. Yes, you can, but there are clever ways to do it. But if you don't want to use double, you can use modern Java language features. And you can use a record. And you can place the update function in the record, and you can see how I compressed the initialization, the update, and the finish by using a record where it does it. And I've highlighted the areas we'd need to optimize. And if we turn this, when we get Valhalla with Jet 401, we turn it into a value record, all the allocations will go away. The new result will go away. The update, which takes an existing result and returns a new result with new values, will go away. You will not have to worry about the allocations because the runtime will optimize it, and the library will optimize the computation and the accumulation. We have to still prove this out, of course, but I think we can get there. So here's the implementation. I just sat on top of a matrix API for MSET. But there's another alternative here. I could implement an LLM implementation like Llama 3 using this matrix API, and I think I'll get better performance than the current implementation does. Now, I don't have time to do this, but given the matrix API is open source, maybe someone else would do it in the community. I don't know. It'd be nice to see. So I think we're onto something here in exploring this space. So there's multiple choices to decide where you want to run and how fast you want to run. All right, so a quick thing about Valhalla. So Valhalla is going to enable more kinds of number. That's one of the key things with respect to AI. So we can think about new floating point types like float 16, bfloat 16, float 8, whatever exotic floating point thing comes along. And we can perform explicit SIMD computations over this data. So while value classes is not yet ready, in the interim, we incubate in the JDK, like I said, with the vector API. But we also incubated a float 16 numeric class in there. So we implemented float 16, numeric value-based class. When Valhalla is ready, we can turn it into a value class, and maybe we can put it directly into the platform instead. So at the moment, it's experimental. But we are actually optimizing this in the runtime hotspot to support the vector API and scalar and auto-vectorization of operations on float 16. So we're really going for it here. So if a Llama model supports float 16, we can start optimizing float 16 computations in Java itself. So the way we're doing this is sort of a low-risk approach to increase mind share and get feedback while we're waiting for Valhalla. Maybe some other kinds of number will come along. We're not sure on the scope yet. OK, on to the last one, which is Babylon, the code reflection feature. So I said in the, how many were at the keynote? Was everyone there? Pretty much. OK. So as I said there, it's really one major use case for code reflection is to reach out to foreign programming models. And we do this by enhancing Java's reflection. And it's called code reflection, which gives you access reflectively to the code in a Lambda body and method body at runtime. Java reflection today can only access your fields, your methods, constructors, but it can't get access to what the constructor contains or what the method contains, and it can't get access to what the contents of a Lambda contains, the code. So we've devised a new sort of symbolic form for Java code, an in-memory representation. It's just kind of like a tree structure, but is sort of optimized for analysis and transformation. You can think of it as similar to Java C's AST tree, but it's designed to be able to reach out more to foreign programming models and to the descriptions of code that they use. So what is the foreign programming model? It's one that is not the Java programming model, that's it. We don't want to add GPU programming to the Java programming model. We do not want to add auto-parallelization of for loops to the Java programming model necessarily. We don't want to specify what auto-differentiation is. I do not want to be, I imagine the Java language specification people do not want to go anywhere near that when they're updating the Java language specification. So how do we solve this? We solve it by letting libraries interoperate with the foreign programming models, and it's up to them to devise the constraints and the specification of how they map Java code to that foreign programming model. We get out the way, which means that we don't have to do that, they can do that, they don't have to wait on us, and we can both move faster. So examples I gave were, given some Java code, you can symbolically analyze it and generate its differentiation, or you can apply automatic differentiation to it, which is important for machine learning. We can go to GPUs that Gary will talk about, or we can generate machine learning models from Java code, as I showed in the keynote, and I can show now. So I talked about ONNX being two things. All ONNX is a way to represent machine learning models in a standard way using protobuf, and a way to execute those machine learning models in an optimal way. So if there's a GPU available which is supported, it can execute the machine learning model on the GPU instead. So all it is a constrained form of computer code and a bunch of constant data and operating on tensors or multidimensional arrays. So this was inspired by Python's ONNX script in the ONNX project. And it has a way to represent ONNX models as Python code that translates to ONNX models in the protobuf format. So here's an example of GELU, which is kind of like you place this in between two networks to smooth it out, the inputs and outputs. So you can see it doing a bunch of operations. I can't remember what this op.erf is, an ONNX operation. I can't remember what it stands for, but I was the error function. I linked to it. So you can see a bunch of mathematical operations. It takes a tensor in X. It does some like NumPy-like broadcasting on it, and it produces a tensor out. That's it. And this is the ONNX model I printed out when running ONNX script down below. It sort of prints out a textual description of what it is. So you can see the constants, the multiply, and so forth explicitly expressed, not as Python operators. So what's going on is it takes the Python AST, the ONNX script library takes the Python AST, it munges over that, and it produces an ONNX model out from the other side. We can do the same in Java. This is real working Java code in this prototype we wrote. So we can represent ONNX models as Java code that translate to ONNX code models. So a code model is a way of representing structurally any form of code. It's like a meta model. And then you devise semantics for the area of the programming model you want. So we can use code models to model Java code, but we can also use code models to model ONNX code. And this is the code model printed out in text that represents our translation of this Java code to the ONNX code model, from which we can then generate protobuf. So you can see how it's actually quite similar to this. You know, it's different textual representation, but we can see there's constants coming, there's a mul, there's an ERF, and so forth like that. That's the ONNX, the pure ONNX code. Now, if I was going to show you the Java code model, there'd be a lot more noise in it, because this is not a Java program represented here. This is the ONNX program. So we can do better. We can get rid of the constants, like so. But we can't use operators. So we're kind of constrained, so we have to say mul and add, and we can't get quite good as Python. I don't know if we'll ever get there for this kind of thing. But it's not terrible, really, at all. You can code like this. So what's going on here is code reflection takes the Java's AST from a compiler, and the compiler translates the Java code to a Java code model and stuffs it in the class file. And the Java code model here, I've shown it here. So this is containing operations that are specific to Java. So you don't have to look at it too close. You just get a sense on it. And at runtime, the ONNX library extracts out that Java code model, and the library transforms it into an ONNX code model you see there that I showed earlier. And then the ONNX library translates it to the ONNX protobuf. And so this is the architecture that I showed. It's similar to all the architecture I've shown previously. Depend on something native, use the FFM API, bind to it, bind to the native library, build a library on top, nothing magic about the library, and then build your application on top of that. And that's what we did with ONNX. We prototyped this. You want to see the demo again? I can show that. I'm going to finish up. I'll quickly show the demo. Okay, so I'll go away. So this is a swing application. You can draw the number in. I like doing 7 because it's the most reliable one I found. So we predict from the image, and there's a bunch of probabilities output from it, and 7 is the most probable there. I mean, you can do numbers. Sometimes I try and do an 8, but I don't know if that will work. So it thinks it's a 3. Hey, you can get better at that sometimes. But the point is, it's a very simple application because we're just learning how to build this library out to prove that we can do this. And the code is really quite straightforward. This model is constructed once by the swing application. We load a bunch of data we call weights that are input into the algorithm. First of all, these weights are obtained from training an equivalent Python model. Then every time we predict, we run this classify method that takes the image data extracted from the swing app, converts it to a tensor, and then executes the machine learning model using a class that we wrote called ONNX runtime. It does the transformations and stuff like that. And the bulk of the machine learning model is this CNN implementation, which is a convoluted neural network, effectively. It's not too magical, but you see these operations like div and constant. Some are taking the input or results of other things, and some are using the weights, like so. It's fairly readable code. It's a little clunky right now, since we're still working this out. And as I showed in the keynote, we can open up the model that was produced as well. And you can see the same names here. Excuse me. The same names and the weights used. So you can see it's a very clean translation to an ONNX model. So we eventually, I hope we can support more substantial applications with control flow. So we can express for loops and if statements in the Java code, and it translates to the equivalent operations in the ONNX model. Maybe we'll get to training at some point as well, but we need a clever math person to do the auto-differentiation for us. Okay, I am 2 minutes. I think I'm actually done. I don't really have time for questions, but you can reach out for me afterwards. I'm at booth duty at 4 p.m. as well, so you want to reach out to me then. And don't forget to go to Gary's talk after lunch. All right, thank you.